today we're talking about quantum computing. Federico looks super excited. Federico is my contact at IBM, so we need to find his own user today. Let's all try to sell components to him. Federico, thank you very much for joining. Sana, are you ready? Let's get the ball rolling. I think we are ready to rock, right? It's going to be a very excellent meeting. I want everybody full of energies. I want everyone to feel that today we are here to find business, to find cooperation, and most important, to meet new friends, to establish relation with already coming friends, like our new guy from from Bautista. Thank you very much for joining. Let's start. Ladies and gentlemen, welcome. Welcome to the 18th Epic Online Technology Meeting on quantum computing. My name is Jose Pozo, and together with Amairi-Pyka, I have the pleasure of chairing this next 2.5 hours. It's going to be a challenge. We have 12 speakers, 2.5 hours, and at the same time, we'll have a meaningful discussion. Epic, thanks to you, is now one of the biggest, I think almost the biggest, photonic industry association, 557 members. Thank you for joining PHIX. It's our latest member. Thank you for joining yesterday, PHIX. We continue growing. So if you want to support us, just join us. It's very simple. Just sign the form. For those of you who don't know, we do three things. The first one, organize meetings, presence and online. Fantastic meetings. We love them. We have a long list of online meetings. Also, when the world goes back to normal, when the COVID-19 seems like, water under the bridge, we organize also present meetings. So I want to see some of you, maybe all of you, in Glasgow, first week of September. We're going to have the World Quantum Photonics Technology Summit with a great program already. At the same time, I also want to remind you that you are Epic members, so you have a long list of market reports waiting for you at the extranet. So all of you, just go to the top left corner of the epic-asoc.com website. You can download 17,000. Carlos is crazy. He counted that. 17,000 market reports, view graphs, charts. All of you have access to download all of that. It's actually commercially available market knowledge that we bought and give to you for free. Of course, we bought a proper license for that. I would like to highlight, for example, that we bought last week, no, 2 weeks ago already, the worldwide market for lasers. This is the market report from Strategies Unlimited. This is the best laser report there is in the market. So you're interested about femtosecond lasers, picosecond laser, laser optics. Of course you are. You should have a look at this market report. Also, all the Epic members have job openings. It's a great time to look for a job in photonics. www.jobsinphotonics.com. This is now the biggest website worldwide about finding a job in photonics. I have a job in photonics, so that Sana, we love our jobs. We got more people to work in photonics. We actively scouted the job openings of all our members, and we posted them in this website, and we are working with recruiters to find people to fill them. So you also know people who are looking for a job, directed where? To jobsinphotonics.com. And that's it. Now let's talk quantum computing. And the first thing I would like to do is to thank our sponsors today. I think they are all very famous, very great companies, but I would like to say something about them anyway. So Toptica, all the way from Munich, but a company that all of us know, everybody who is a geek in photonics, a geek in lasers knows Toptica. And Toptica develops and manufactures high-end laser systems for scientific and industrial applications. The portfolio includes their lasers, ultra-fast fiber lasers, terahertz systems, and frequency comms. These systems are widely used in quantum optics, spectroscopy, biophotonics, microscopy, as well as test and measurement. I also would like to say hello to my friends from Helia Photonics, all the way in Glasgow. Helia Photonics offers services, advanced optical coatings, and cheap facet polishing services for quantum applications, photonic integrated circuits, PLCs, micro-optic components, SHG crystals, and cryogenic optical cavities. I also want to say hello to my friends in Enschede, PHIX. PHIX is a great company. You guys have to go to visit them. PHIX has experience in packaging and broad range of materials, including silicon, silicon nitride, silicon insulator, indium phosphide, gallium arsenide, lithium niobate, polymers, and any other material. Actually, anything that you want to package, these guys know how to package it in a scalable volume production suitable. They are fully independent, and they perform peak packaging to a large range of applications, including LiDAR, quantum communication, biosciences, you name it. I want to say hello also to my friends in Delft. Great city. I lived there for a long time. QuTech is the leading R&D center now in quantum technologies worldwide between TU Delft and TNO. They do advanced research for quantum computing and quantum internet, funded by Delft University of Technology in the Netherlands. It's a great place to visit, and if you're curious about R&D activities in quantum, visit their labs, an unforgettable experience. And finally, I want to say hello to Finland. This looks a bit like Eurovision today, right, Sana? I want to say hello to Finland. VTT, Technical Research Center of Finland is a non-profit government organization operating under Finnish Ministry of Economy, but at the same time, they are a leading center in silicon photonics, especially when it comes to the broader, to the thicker silicon, the one that is transparent in the visible. They do great things in biosensing, but also great things in quantum, and they have great activities in the packaging side. Thank you very much for these 5 sponsors. You rock. And the next stage is to talk to you about the amazing program that we have today that combines photonic integrated circuits, that combines lasers, that combines detectors, combines end users. When I see the agenda like this, I'm like, interesting. But when I see it like this, I'm like, great, this is what it is. We have mapped every company that registered today in what we think, this is our opinion, what we think it is the right position in the supply chain. Of course, we identify possibilities of working between the packaging and the photonic integrated circuits, between the lasers and the optics, between the end users and the rest of you. The idea here is to find ways of working together. Notice that we have, for example, companies that make nanotechnology, companies that make software like Quantum Benchmark, companies that make different components like AMS technologies. This slide reflects the companies who register to the meeting. I never forget any of these 557 members. So if any of you feels that the logo should have been there, don't think that I forgot you. I will never forget you. Please register to the upcoming events. And with this, I would like to also remind everyone that this meeting is broadcasted in YouTube, in the YouTube channel, in the YouTube universe. So I would like to say hello to all the YouTubers. If you want to contact any of the participants today, all you have to do is send me an email, jose.pozo@epic-asoc.com, jose.pozo@epic-asoc.com. Send me an email and I will introduce you to the participant you want to speak because you can do business. This is valid for the YouTube channel as well as, of course, the Zoom channel. So all of you want to be introduced to each other, all you have to do is send me an email and start your business. That's all I have to tell you. I try to be as fast and as efficient as possible, just to give you an example of how I expect you to be during the meeting. Thank you very much. I think it's time to introduce now our first speaker today. And this is a company in Palaiseau that is the one that started EPIC in quantum. The company Quandela. One day I met them at a conference. They showed me what they did, and they showed me, well, we are specialized in the single photon sources. And I said, do you want to be the first EPIC member on this? And they said, yes. So Quandela was our first EPIC member in quantum technologies. Now we have about 100 companies active on this. So they started the moon, and for that, I am eternally grateful. Thank you very much for being with us this afternoon. The attention of everyone goes to Paris, goes to you.
Hello. Hello, Jose. Thank you very much for the introduction. I'm very happy to be a member of EPIC. It's a lot of benefits. Thank you for this introduction. So I will try to be fast because the time is short. I have 6 minutes to convince you that Quandela is building photonic qubits. So we emit single photons based on using quantum dot-based single photon sources. So I will not enter too much into the details. It's a session about quantum computing, so you know that we can develop quantum computing based on different platforms like atoms, ions, superconducting qubits, circuits, many things. Here in Quandela, we believe that photons, it's also a strong platform with a lot of benefits to develop quantum technologies, and will be at the heart of the quantum revolution. First, because this is a flying qubit, so it's easy to transport quantum information. So this is for the development of a quantum internet using optical fiber, satellite communications, for example. Then it's super easy to manipulate and control the information that is stored into the photon. For example, you need to change the polarization. That's super easy to do. You can do it at room temperature. You don't need any vacuum. You don't need any big stuff. It can be done on a very small chip. And it paves the way to modular design. Then the coherence of the qubit is super long, actually. As long as you don't kill or lose the photon, it's super long. And then, as I will show you, it's very flexible. You can generate quantum states that are called cluster states that are very fundamental components for universal quantum computing, and that's super easy. We did it in fibers. This is what I will show you at the end of my talk. So basically, if you want to develop a quantum optical processor, you have 3 parts. first, this is where Quandela is, we generate qubits, so single photons, and we insert the photonic qubit into an optical fiber that is connected to a quantum processor. This quantum processor is usually made of silicon or any other material, glass, for example. It works at room temperature, and in this processor there are gates, and these gates are controlled electronically using a classical computer, basic stuff. And then you have photons that are getting out of this chip through a fiber, and you can send the qubits along long distance, or you can measure and analyze your quantum information using single photon detectors, for example. And then like this, you can have a feedback. This is a continuous flow of qubits using that is traveling through the processor. So now there are many startups, many people doing this kind of stuff. So it can be done on big optical tables. So it takes a lot of space, but it is very convenient to do a lot of fast experiments. And now a lot of companies like PICs or Xanadu in Canada or QUIX in Netherlands are designing chips that are very small, very compact on different materials. So silicon, silicon nitride, glass, for example, and can be done in any foundry. You can design the chip, and it takes few centimeters. You connect all the fibers, and that's it. There is a Moore's law, actually, for the number of components that you can have on a chip. Actually, we have seen that every 4 years, the number of gates, the number of components that you can have on a chip is multiplied by 100. So you can imagine that in 2022 or 2026, you will have many, many components on a chip like this. And this is a key for optical quantum computing. Then the other key is the emission of photons, so the quality and the number of qubits that you can have on the chip. And this is where Quandela is. We fabricate sources based on semiconductors, so very compact, few microns size. They are coupled into single mode fibers, and they emit a high stream of single and high quality of single photons, such as you can have a lot of qubits in your devices. And we have very recently published that we are able to fabricate with a high reproducibility these devices. So a lot of key features that I will not enter into the details. I don't have time, but this is a state of the art in terms of photonic qubit sources. That is the key to be plugged into photonic on chip, into chips. So few applications, for example, that was published last year. Here we used one of our source. Then we used a demultiplexer to have many channels and was connected to a 3-channel photonic circuit. If we compare the performance between a laser and our device, actually we saw that it's almost 100 times faster with our device that we provided to the consortium. Another example here, it's a collaboration with University of Jerusalem. We have our device that emits qubits that are linearly emitted one after each other. And they have developed a sequential entangler in order to generate cluster states. And with this, we have seen that with the high efficiency of our device, it was possible to increase the number of qubits that was possibly entangled together, while with old generation of old sources, it was impossible, because with a laser, it would have taken years, while with our device, it was possible to entangle several qubits within hours. So just to tell you that we wonder these kind of things possible because of the high efficiency of our device. Now we are working on the integration of a lot of chips in this kind of device that is data center compatible. So in this, there is a computer that's only here to do the control, to check that everything is okay. It integrates lasers, the optical processors that I've shown you, optics, because we always need optics, filters, stuff like that, electronics also, because we always need electronics to control and stabilize the system, and the sources that are in the bottom rack. Inside there is a very small cryostat, doesn't need any power, doesn't need any helium stuff, just electricity a plug on the wall, and that's it. And with this device, you can have many of them, and you can start first calculations using photons. And you can also transfer the qubit from one to another using optical fibers. So this is the magic of the photons as a qubit. So here I am. Quandela is a three-year startup based in Paris. This is growing fast. We have more and more customers. We are trying to have many new products. This is why we're trying we need to collaborate with people that use to fabricate photonic integrated circuits, like maybe for QUIX. We already work with them. Optical filters, because it's super important to filter the laser without losing our qubits. We're also trying to fiber everything that we have. So in order to make everything more and more compact, such as it will be very super small at the end. So thank you. I hope I'm not too late. That's fine. Yeah.
It was excellent. Thank you so much. This is really amazing technology you're presenting today. And it's nice that you show what is that you're interested in. We have here photonic integrated circuit expert a lot. We will see already a talk from QUIX and talk from VGT, but I also will see a talk we have here with us from Icon Photonics. He can also give a word about that. Do you have a question to Valérian? Anybody? You can just unmute yourself and ask, please.
Yes, this is Thomas van Nels from TechnoBiz. Can you elaborate a little bit more on the kind of requirements you have for packaging or PIC design issues that you currently have?
Yeah, thank you for your question. So actually, we need to integrate gates on chip and to have interferometers in order to do operation on chip. And this we don't, as you can imagine, with single photons, we don't like losses. So we need to have the most transmittive chips that are possible, and to have a good coupling with the fibers input and output coupling, as you saw, because we need to travel. So we need to enter into the chip and to get out from the chip to get to another device or to get to detectors.
Yes, please.
Schell, Fraunhofer, thank you for your talk. Is there any perspective in getting the operation temperature higher? I read in one of your Douglas 8 Kelvin. Is this a limit, or how high can it get?
Yeah, thank you for your question. This is a limit, theoretical limit. At higher temperature, actually, the semiconductor is not pure anymore. I mean, we have a lot of vibrations in the semiconductor, such as it introduces a lot of noise in the photons, and then the photons are not qubit anymore, they are only photons. Because we need to have a high coherence, a high purity of the photons in order to make them interfere, for example, or to have entanglement. If you increase the temperature, it will be impossible to have entanglement with a large number of photons.
Thank you very much. Anyway, in the quantum field, temperature is the noise, right? Nobody wants that. So allow me to go to the next speaker, because we have now Quantum Benchmark. We have Joseph from Quantum Benchmark.
Yeah, I'm here. Oh, I got
yeah.
unmute.
So because for quantum technology, very important is the software as side by side with the hardware. So now you have the floor, please. We didn't, did we try already? We tried sharing already, right?
Yeah, I can share, no problem. All right,
excellent.
So let me go in here, share screen. Where are we? That's, nope, there we go. Okay, well, thank you very much for the opportunity to tell you about what we're up to here. Can people see my screen? Oh,
yes.
Good, great. Okay, so Quantum Benchmark is 3 years old. We basically build technology software that allows both makers and users of quantum computing to get the maximum possible performance out of it. So something people with the traditional classical computing background don't understand is that there's some very unique challenges with quantum computing. which is analogous to the following. For your designing trains, think about trains as like classical computers. They follow a definite track. They're deterministic, and you just have to design, the engine to throttle the speed and so on. But when it comes to a quantum computer, it's more analogous to a rocket ship. You are navigating through a three-dimensional space in the case of a rocket ship, and there's a whole new challenge around control, which is making sure that you're monitoring and error correcting the trajectory so that the rocket ship goes where it's supposed to go. This is not a problem you have with trains. This is a problem you have with quantum computers. Quantum computers can take us to totally new places, but they have a unique challenge, which is that the quantum nature of the computation is very error prone, and it's an analog control problem. So we have to navigate in a continuous space. Unlike the zeros and ones of classical computing, we have qubits, which have a continuous amplitude. And so there's a big challenge around navigating the computation, designing the hardware, and that's what we help with. We have a team consisting of the world-leading experts in this problem. We have two products which help this process. So we have a design tool which we provide to hardware makers, people designing quantum computers that actually have qubits. It doesn't matter what platform, whether it's superconducting qubits, ion traps, semiconductor devices, photonic quantum computers. We work on all platforms. And what it allows the designers to do is understand where the errors are occurring and to combat them to provide the best possible, most stable computation to users. And we've currently saturated the North American market, and we're now expanding into the European quantum computing market. So basically, every big name in quantum computing is our customer already because of the tools we provide. And some of the tools we provide this kind of diagnostic information. This is just a sample from IBM's public device, their Yorktown chip. You have 5 qubits. We're looking at a qubit gate on 0 and 1, a 2-qubit gate on 0, 1, and idling the other 3 qubits. You won't understand everything in this figure, but just to give you a sense of the complexity, the colors in this figure represent how strong the errors are and where they occurred. And what's noteworthy is that the reported error rate, it just corresponds to the errors occurring in this column, which is the errors from the C0 gate itself. And that gives a 2% error rate. But it turns out that the errors that dominate the computation are these other errors that are not reported, which are detected by our software. And so this gives a 20% error rate per computational step, which is 10 times bigger. So the point is ultimately to deliver better hardware performance, you have to address all of these other errors that are hidden beneath the surface. And that's what our software does. And that's why basically everyone is using our tool, because of its usefulness in detecting this complex error problem. What we're also doing is launching a compiler and API for users of quantum computing, companies exploring the research capability of quantum computers. And this is our TrueQ API and compiler. And basically for all applications, whether it's optimization, machine learning, drug design, quantum chemistry, transport problems, for any of these problems, we can take the natural representation of those problems and modify it and error adapt the algorithm to minimize the impact of the errors on any hardware platform. And so this is a very useful tool. It provides users with the know-how to navigate the space of quantum computing. And we're very excited about the success we've had with that. So this is just an example of what it can do. Here we show the five different 5-qubit chips, IBM's public chips, and we use our tool to assess the capability of each chip to perform different classes of algorithm. And what you see here on the x-axis is the circuit depth. That's how long it takes to compute the solution to the problem. And on the y-axis is the precision that that chip can offer for that problem. And what you see is that with 2 of the chips, London and Burlington, the error is basically, the imprecision of the computation grows very rapidly. And so you basically can't compute beyond 1 or 2 operations. And what you see, the best performing is Vigo. So the Vigo chip basically shows that if your precision required for the computation is say 0.4, then Vigo can compute all the way out to about 15 computational depth, which means it can solve much bigger problem instances. You can add many more nodes to your optimization problem. You can handle bigger data sets. You can handle bigger molecules. That's what this corresponds to. So this is just one aspect of what our software does. It allows the users to understand which hardware chip can perform best for their application, which is critical as we're aiming for quantum advantage, where we have to really squeeze every possible ounce of performance out of the processor and find the best co-design fit between algorithm and hardware performance. And with that, I'll say thank you for the opportunity to speak.
Thank you very much. When I got your request to give a presentation at an EPIC meeting, I was so excited. And that was actually in my expectations. Thank you for a great presentation. Remember, EPIC is a photonic association. We love photonics. We are passionate. I cannot sleep thinking about photonics. You're at a photonics meeting. I have here the entire supply chain. So what I'm going to do is I'm going to introduce you to a couple of friends that do great things in photonics for you to have an idea of the kind of companies we have in this network. The first one I would like to introduce a company I went to visit in Paris, a company called Prophecy. When I went to ask them what you guys do, they told me, we want to give vision to the blind. And I couldn't breathe. Simone, thank you very much for joining. What's Prophecy? What are you doing at this meeting? And what kind of cooperations would you like to start?
Hi, hello everyone. Simone from Prophecy. For those who may not know us, we are a startup based in Paris. We do image sensors based on silicon, but we don't produce frame-based sensor. We do neuromorphic vision sensors or event-based sensors. So we are trying to do silicon retinas, not to apply to humans, but also to machines. So we are not really in quantum computing. The reason why I joined this meeting is because I'm curious to know the status of, let's say, research, and not only research in this field, to see if this can be applicable to some of our future development. Ideally, yeah, including some part of the computation directly in light before moving to classical, let's say, electronic computation.
It is one of the most exciting company visits I did when you saw me the demonstrator, the amount of actual things you could count with your machine vision equipment. I want to introduce also our new friend from Quantum Benchmark to not only small companies, but also large companies. Coherent is a member of EPIC, and my friend Mantas joined the meeting. He was one of our keynote speakers at the last meeting in Barcelona. Thank you very much for joining. What did you join today? What kind of cooperations would you like to start?
Hi, everyone. So I'm basically working as a program manager for ultra low noise laser systems that are used for cooling and trapping cold atoms. So we basically involved, in the scientific market related to quantum technologies. We're not doing anything with quantum computers, but as part of my job, I'm basically looking into kind of future markets, right? Especially from the side that's related from photonics. And this is to get idea for our future product roadmaps, essentially. So trying to learn the trends and what's going on and what's going to be happening, in the next few years. That's why I'm here.
At the end of the day, this is a market that's going to be driven by who's making the most efficient 400-ish nanometer laser. What is the push for Coherent on that? Is there a strong R&D lines? Are you looking for new cooperations?
So we do have some lines. They do not provide those parameters that are needed for quantum necessarily. So they merely used for other applications and biosciences and so on. But that's one of the things what we want to estimate and understand. The market sizes and what investments we do need and what potential kind of returns we will have in the next 10 years. So that's the things we try to learn and understand now.
So Joseph, as you can see, we have the entire supply chain here. The idea is to interact with companies who can make quantum computers. Later on, you're going to hear the presentation from Federico from IBM. I already talked to him quite a lot on the phone, and it's quite outstanding. Thank you very much for presenting the software side. It helped us opening the eyes of what we are enabling with the photonic innovation. Thank you, Joseph, for joining. And we go to the next speaker, who is great to have her at EPIC. AMO is one of our EPIC members in Aachen, and Lena has been interacting with EPIC already for as long as I've been at EPIC, and she's always very active at our meetings. Thank you very much for joining us today, both on the nanotechnology as well as on the silicon photonics. AMO is one of the great members that we have. The floor and the attention of everyone is yours.
Hello to everyone, and thanks to the organizers for inviting me to this exciting meeting about quantum computing. And I will let you know what is going on at AMO about quantum photonics. We are located in Aachen, Germany, and AMO is a high-tech non-profit SME. And we've been active as a research foundry already for over 25 years. and during the last couple of years also been active as a quantum photonic research foundry. And this we do with our almost 20 years of experience in silicon photonics and our close relationship to the Technical University in Aachen. And as you can see here in this chain of research, you see that we are mainly active in the fields of applied research and prototype development up to the small scale production. And this all is based on our silicon technology, which was mainly been used for nanoelectronics as well as for photonics. So what we offer to our customers is customized prototyping as well as contract research. And we do all this in this beautiful building over here. We operate our own clean room here for silicon photonics pilot line, which I will show you some slides later a little more. So why we think light-based quantum computing is exciting and this also has definite advantages over the some of the current matter-based approaches. So as you might know, so the recently shown quantum computers are all based on matter. So all these different kinds of approaches differ very much from the approach of integrated photonics, where we want to go for an all photonic chip from the source on the quantum processor up to the detection side, so that we can do both the photon generation, so the entangled generation, the quantum processing, as well as later analysis of the results on one single chip. And as you might know, in order to make a quantum computer useful, also the number of qubits is much higher than the number of qubits shown with matter-based systems so far. And as you might know, light has many advantages because photons can be really easily manipulated. And with the photons, we can use all our photonics technologies developed within EPIC and also by other EPIC members during the last years. And the photons are, as you know, intrinsic carriers of quantum information. And with silicon photonics, making real advances during the last years, also manufacturer platform is generated here. And as well, the problems with decoherence of the matter-based states does not happen when you use light for quantum computing. And of course, the aim is to go for the application at room temperature, which might not be happening, but at least to go away from the very millikelvin range of matter-based quantum computing. So we believe that integration is really the key, as it has been shown with microelectronics in the 70s, and the integration will only the integration will lead us to a disruptive technology change in the future. So what Amado does on this side is we have all the components ready to be used. And these components are based on silicon photonics, well as silicon nitride photonics, that we can make use of low loss waveguides, phase shifters, modulators, can have the sources for entangled photons right on chip with microring resonators, for example. And we can do high order filtering of pump light, for example, can have delay lines as well as a detection on our chips. And this is all possible on a rather large scale, so wafer scale manufacturing is, of course, comes along with silicon photonics. So what we're looking for within this meeting, as well as in the future, is to dive more into the world of quantum science. As you can see here on this mind map, many important topics of today's world can be solved or maybe tackled in the future also with quantum systems. And we are looking for industry partners, small or big startups, research partners, universities, whatever. So really innovative people here who also think that every photon counts, and as well that we want to help researchers out with our rapid prototyping services, and we offer this customized fabrication runs to try out new technologies to be a testbed for futures quantum computing based on photons. Thank you very much.
Thank you so much, Anna. You are in the right place. It's full of institutes here, and all the people that will be able to collaborate with you on this. And allow me to introduce before we first. Let me ask: is there a question to Anna? You can just unmute yourself. Okay. Otherwise, please let me introduce to you Carlos from Icon Photonics. Hi, Carlos.
Hi, everyone. Thank you very much for these nice presentations. Yes, so we are from a startup created in 2018, located in Paris, east of Paris. We deal with packaging and fiber coupling challenges. And my reason to be here is to understand also on the quantum domain these packaging and integration issues, that to see if our solution, which is a polymer-based solution that we use for fiber coupling, so to see if there is some alignment, some synergies that we could help on these aspects.
Thank you so much, Carlos. So now we know what Anna wants, and there's a question from IBM, also CNM. How are you doing, Yad? Oh, I don't hear you. I'm afraid I don't hear you. So you are unmuted for sure. We still don't hear you. I don't. As long as I'm laughing.
As soon as we solve it soon, just post your question, just post it in the chat, and we'll give you the microphone later.
Maybe I can help out with a question in the meantime.
Yeah, sure.
So I would like to ask, where's the current limitation in terms of fabrication? It seems to me that it's still some kind of manufacturing, like fiber attachment and all that. So what kind of quantities could be produced currently? And is there a plan to scale it up maybe later on once the first commercially applications for quantum computers are available?
Yes, also, I mean, the size is always a good question. I mean, it very much depends on the customers. So pretty much we go from having small quantities like a couple of chips to having a full batch wafers. So up to 25, 50 wafers for one single design, where definitely an automation of the later on packaging might make sense in the future. Yeah.
Thank you so much. We can try again with Jad. Yeah.
Okay. It's okay now?
Yeah. Now I hear you.
Okay. Thank you very much. Well, I would just to answer for the request. Okay. At the CNM, we have a large experience in the nanofabrication for photonics chips. So our next imminent step is to work about the quantum technologies. And our expertise by now is the silicon nitride. The point is that, as I have seen in the scheme, you are like working on the, let's say, short amount of chips. In our institution, we are able to fabricate a medium to large production. So the normal fabrication process we have is like to fabricate from 6 to 10 wafers at a time. this is just using the I-line stepper. So if we combine it with other technologies, it could be considered as massive production. So if you are interested, we can be contacted by Jose Pozo, and then we can arrange what the next steps if you want.
That's great. Everybody who want to contact the other can just write an email to Jose. He will leave his email if you don't have it already in the chat, and you can just write us and we put you in contact with the person you need. Thank you so much. Please let me go to the next speaker. You wanted the research institute. This is a big research institute in Germany, one of the biggest with already a lot of collaboration in quantum computing. They helped build the first quantum computer in Europe, to my knowledge, together with IBM. Please correct me if I'm wrong, Federico. And now we hear the talk from Martin Schell from Fraunhofer, HHI. Here you go. Did I say any mistake? No. I think I'm right.
1 second.
That's good.
Yeah, thank you very much for the introduction. Unfortunately, I have to correct you a bit. We are very popular, have lots of experience in quantum key distribution and quantum communications, but so far very limited experience in quantum computing, and that's one of the reasons I'm here.
Oh, my bad. That's good. That's good. You're here to correct us.
I would like to explore the possibility to do something also in quantum computing. Our major capabilities is photonic integration, and this is an overview of a couple of examples what we have done with our indium phosphide monolithic integration platform. This is online for customers since 5 or 6 years, so it's we are quite experienced. These chips are have very different applications, from communications over sensing. Different customers, roughly 50% still goes to institutions, universities, roughly 50% nowadays go to companies for commercial use. And we have heard the silicon photonics talk before. We're probably gonna see some talks about silicon nitride. Big advantage when I put indium phosphide monolithic into that context is that with indium phosphide monolithic, you can co-integrate both lasers and detectors in a monolithic process. And it's one of the more experienced technologies, more mature technologies. Disadvantage also is that the dollar per square millimeter is probably the highest among these 3 platforms, and so you should be careful about the pricing. The entry hurdle is quite low, simply because we have very mature design kits, and even customers who come from the electronic world can design their own photonic integrated circuits with a couple of weeks training. This is one going into computing example, which was designed by Bright Photonics, just to give you an overview of the capabilities and what we do here at HHI. This is one quantum photonic chip, which is a couple of years old already, designed by a customer and for quantum key generation. And there's a couple of other quantum projects we have served with the indium phosphide fabs, but we are not allowed to talk about that. This is again computing. That's all optical neuron that we attempt from Princeton University to implement all optical convolutional neural networks in photonic integrated circuits, and they did their first trials also with our fab. And last but not least, one of the, it's a bit at the edge of photonic integration. If you do something in silicon nitride or in silicon, which in order to benefit from the much lower loss dB per centimeter compared to indium phosphide platform, at the beginning you have to couple a laser into it, and at the very end you have to couple it out into a photodetector. And this coupling process is one of the cost drivers when you go to volume applications. It's also critical in terms of performance. It doesn't make sense to fight for each 0.1 dB in the circuit when you lose some 30 to 50% in the coupling in or coupling out. And there we have lots of different experiences with different silicon or silicon nitride platforms, how to couple in or out indium phosphide from such a passive waveguide. these are the things we can contribute to any photonic computing project. And in quantum key distribution, I would consider HHI also as very experienced in system design. So we know different concepts, and we can then find ourselves have our own ideas how to translate which of the concepts into which kind of photonic integrated circuits. In quantum computing, we do not have these system know-how, so we would be very interested in some people, some groups which are very knowledgeable in the system design, what to do, who can give us some guidance in how to use our big capabilities for quantum computing, rather than doing that ourselves. What I have not yet mentioned is our polymer photonic integration circuit. So this is passive hybrid integrated circuits where we co-integrate lots of nonlinear materials in order to do parametric spontaneous bound conversion and all the other effects which you can use for quantum key cryptography. So once again, we are very interested in common research projects in quantum computing. I'm personally also interested, it's probably not the right crowd here, in non-quantum, but optical computing. And of course, we are happy for everybody who gives us guidance into what direction to develop our capabilities regarding quantum computing. And of course, we are also very happy about getting new customers. Thank you very much.
Thank you very much, Martin, for a great presentation. It was great to hear from Fraunhofer HHI. I must congratulate you on the collaboration with IBM. It's actually broadcasted everywhere. Everybody's talking about that. One thing that I'm getting a lot of questions after your talk, there's a question from somebody, I think a common friend called Carlos. He's asking, if you were going down in an elevator for 30 seconds, you could use 30 seconds to explain why PIC is required for quantum computing.
Oh my God, let's fire back. 30 seconds. Oh, if you want to use photons for quantum computing or any quantum stuff, the phase is extremely important. And if you think about implementing something in the real world, you want to have a phase stable over years and over different temperatures and over different aging statuses. And you don't want to put one PhD student besides each quantum photonic implementation. So that's a big benefit of photonic integrated circuits. You have something stable and you can go away, switch it on again, and you have a very good chance that it's still stable. Was it longer than 30 seconds?
It was perfect. For me, every time people ask me that question, I show the picture of the optical clock bench setup from PTV, and then I show a photonic integrated circuit from Fraunhofer HHI. And people get like, oh, of course. One thing, people keep asking me, what is the coolest the thing that you have seen in photonic integrated circuits? And I keep talking about the hybrid laser platform. This is coming. This is now a mature technology combining polymer with photonic integrated circuits. I know that Fraunhofer HHI is bringing this to a commercial offer. Could you comment something on that?
So just to be correct, we don't bring that to commercial offer. In this case, Lionix is a company bringing that to a commercial offer. But there's different niches in photonic applications when you go to very high volume, and this is very high datacom volume with a couple of 10,000 pieces per week. Then hybrid integration of different materials may suffer a bit too much from the cost of assembly. In quantum computing, I'm afraid that, even also in quantum key cryptography, the very large volumes will be so far out that I'm going to be retired before they become reality. And until then, I think we can still, if you don't do hybrid assembly, we should not worry about, or when we decide to use hybrid assembly or not, cost is probably not an issue. It's just about performance.
Martin, since I know you, you've been correcting me with everything I say. So allow me to correct you once, just once, because you say that you're going to retire soon before there is volume production of quantum computing. So I'm going to introduce you to a friend of mine. We have Jose Capmany from Ipronics today in the room.
Yes.
Yes.
Yes, we do.
So we've been talking about programmable photonic integrated circuits for many applications, and you told me in 2 years I'm going to be in the market. Can you tell what Ipronics does and wants to do?
Well, actually, what we propose is to a device which is similar to an FPGA, And you have the optical core just behind my head, okay? It's made of a waveguide mesh of connected tunable couplers or tunable MCIs, and surrounded, and this is important, by high performance blocks. And this thing, and depending on your application, it can be neural computing or it can be quantum computing. So it might be those delay lines or single phone integrated source. The important thing is that you have a technology agnostic reconfigurable mesh here that you can use to implement your circuits, also to program them, but also like in quantum information, importantly, to program where you want to have your ancilla bits, for example, qubits, because quantum structures would need you need to examine ancilla bits and manage them. So that's the proposal for my products. It's like an optical FPGA for whatever application.
It is one of the most exciting things I have seen in quantum technologies, but also in programmable photonic integrated circuits. You are already talking to many of the foundries. I think I know you already know HHI very, very well. You know even the PDK very well. Can you work with the standard PDKs, or does your design require further complexity and you need to talk to the companies actually making the material and the growth?
Well, yeah, in principle, it for the very basic designs, it can use standard components, but we'll have to evolve this a little bit because we will need to, depending, as I said before, on the applications. For instance, not in quantum, you will not put amplifiers there, but in other applications or in neuromorphic, which is another area which we are pursuing, you will need nonlinear elements as well, but that is outside the mesh. So yeah, we will have to do some a lot of work on that. That's this another part of the exciting.
This fully fits the quantum program of Fraunhofer HHI, so I think the two of you should have a discussion if you are not already talking. Let me introduce you another company who I think is going to go in volume production of quantum technologies very quickly. We have the company QSight. Domenico, how are you doing today?
Very good, Jose. Well,
what did you think about what Martin said, that he's going to retire before we go into
actually, Martin showed one of actually the first chip we produced with them. It was actually before we founded QSight. And now we actually quite improved the technology, shrink the dimensions. And I mean, we are actually working on quantum random number generators. So that's for quantum computation or many other applications like cryptography or high performance computation.
Another great startup in photonic integrated circuits doing quantum random number generation. Thank you, Domenico. Martin, I have a question from the YouTube universe. Everybody's watching us today from a company called Effect Photonics in Eindhoven. Aaron Alvarez Mejia is wondering, is quantum computing with photons at all possible using a single PIC platform? For example, photon pair generators require non-linear materials and single photon detectors require non-centrosymmetric crystals.
It's an excellent question, very difficult to really give a concise answer. So there's a large share of the optical functionality which you can do with purely passive waveguides, and you have seen a couple of pictures here during the talks. Hierarchical Mach-Zehnder or anything structured, but doing really everything in a single PIC material, I would doubt very much, unless you make it, and it should also be the best result possible, because in no scenario you may waste, you should waste photons. So it's, I think the best material systems for quantum computing is a combination of 2 or 3 different material platforms.
Thank you very much, Martin, for a great presentation. We could talk for hours, and if anybody's interested about the isolator they're integrating in a photonic integrated circuit, you should check what they are doing. That's a topic for another meeting. Thank you very much, Martin. Thank you for
so
being
much.
the board of directors
Thank
of
you.
PICs. Thank you. We move to the next presentation. We go to Enschede. We go to the Netherlands, and we talk to QUIX, a startup on reconfigurable photonic integrated circuits using silicon nitride. Thank you very much, Caterina, for being with us this beautiful, beautiful afternoon here in the Netherlands. The floor and the attention of everyone is yours.
Yeah, thanks for the introduction, Jose. Can you hear me?
Loud and clear.
Very good. Okay, so I'm Caterina Taballione. I'm a quantum system engineer at QUIX. QUIX is a spin-off of the University of Twente that was founded in 2019, so we are a very young company. And our goal is to provide quantum technology solutions based on silicon nitride photonic integrated circuits. So here in the first slide, I wanted to put already a picture of what is our main product right now, that it's quantum photonic processors. So we already have heard this name in this meeting for a few presentations, so that's good. Maybe I don't have to go into detail. So a quantum photonic processor, basically, it's a reconfigurable photonic chip that enables you to implement any arbitrary unitary transformation. And what basically this means is that your reconfigurable photonic chip is an on-chip large-scale tunable interferometer. That means that it's phase stable, and then means that you can scale it up, which is good for quantum information processing. And the thing is that you can interface the quantum photonic processor, of course, with single photon sources and single photon detectors. And with this type of setup, you can achieve, well, what is known as linear optical quantum computing. So this is the field that we place ourselves in. The QUIX photonic processor is characterized by three main properties. Let's say it is low loss, thanks to the silicon nitride waveguides that we use. It's plug and play. That means that we work on the hardware, but as well on the software interface. And it is fully reconfigurable. So you can think of it as that resemble, let's say, a sort of multi-purpose optical FPGA. Now, the material platform that we use is silicon nitride, and this makes it possible to achieve propagation loss as low as 0.1 dB per centimeter. We can benefit from the maturity of the triplex technology that has been licensed from Lyonics. This means that you can achieve a very good compromise of density of components on the same chip, but also low loss. Furthermore, the silicon nitride platform has a wide transparency window that goes from about 400 nanometer to 3.7 micron. And this means that it can be interfaced with all common single photon sources, going from quantum dots as Quandela to nonlinear crystal, SPDC sources exploiting, I don't know, a second harmonic generation, or waveguides, passive waveguides exploiting for wave mixing, for example. Another property is that our device is plug and play. This means that the chip is electronically and optically packaged, allowing for easy integration, and that we have low loss fiber interconnect. And here on the right picture, you see actually the inside of the box that I showed you before, where you see the assembly of the chip on the inside and all the fiber arrays bonded together and the electronics. And this step of the assembly is done by PHIX. Every chip is thermally stable, and all the heaters can achieve a full 2-pi phase shift. And this is what makes it then a universal photonic processor. Furthermore, another property is that given by the plug and play is that we can easily swap in and out different assembly inside the same box. The box, and therefore the photonic processor, is remotely controllable because we can plug from a USB cable from the box to a laptop, where then you have the software interface for which you can reconfigure and reprogram your photonic processor. Last but not least, as I said, the QUIX processor is fully reconfigurable. And this means that the interferometer is realized as a grid of tunable Mach-Zehnder interferometers and phase shifters. And well, this is just maybe a particular comment. We use a so-called Clement scheme to resolve this grid. And then you can measure classically and in quantum, so with single photon source, the processor, and you can achieve high transmittivity and high fidelity. So there are a lot of applications for these quantum photonic processors, which are not only quantum. So for example, you can use them for matrix multiplication as well as a large multimode interferometer, or for machine learning. And also, of course, for quantum information processing, quantum mechanical simulations for the materials and molecules, for example, and quantum key distributions. Now, as I said, if it was not clear enough, so our main product right now, we are very young, so we are focusing now on the photonic processor, and we have it available for various mesh sizes from 4x4 to 16x16 modes, and you can use the same quantum box to switch in and out different photonic processors. But of course, we offer also customized solutions, as we have available all the building blocks for photonic integrated circuits. So a bit of our future plan, as we are a startup, we look to the future, and we want to scale up the size of our interferometer up to 50x50 modes. And of course, as a long-term goal, we would like to have, of course, a full integration, a self-consistent system with sources and detectors. And for us, it's very important to expand, of course, our team and the network of collaboration with all the companies that works in related fields of ours. So with this, I would like to thank you.
Thank you so much for the great talk. It's really amazing. And we will hear more about this photonic integrated circuit with silicon phosphide. And I would like to see if someone have a question here for you. Okay, if not, I would like to introduce a friend of EPIC, Hannah. Where is she? Yeah, Hannah from Aarhus University. How are you doing?
Hi there. I'm doing good. Good to see everyone.
So you do more packaging, right?
I'm with the JEPIX and the JEPIX pilot line. So we're currently working to enabling pilot production maturity of indium phosphide PICs. And we're hoping to integrate the supply chain that we have here within Europe a little more and make things more efficient. So speaking towards sources and detectors that can be realized on indium phosphide, that would be a nice opportunity to get active there. So JEPIX, I'm pretty sure most people are aware of, is trying to give companies and researchers like a low threshold entry to the PIC design and manufacturing ecosystems. And in that sense, we can offer, especially with the pilot line now, support for PIC development and also with the orientation in the ecosystem. So we have partners with software solutions, design houses, and even universities that can help with initial feasibility studies. Some of our partners are present here as well. And Martin Schell has already made an excellent point for advertising for indium phosphide and the monolithic integration technology. So thank you. What we are looking for is basically anybody who wants to get active in PIC product development and actually take their PICs to the next level in product maturity.
Thank you very much. We have a question from the YouTube universe to QUIX. Actually, it's not an easy question. I'm gonna warn you already. From Smart Photonics, Damiano Marseilla is wondering, in terms of qubits, how many qubits correspond to the n by n interferometer?
Well, strictly speaking, I mean, to to realize a qubit, you need first of all to realize a superposition. So at least that you send your photon in a superposition state. So for an n by n, that means n input and n output that corresponds to n over 2, roughly. Then, of course, you have to take into account that from superposition, you have to implement entanglement, and that requires some gates and ancillary qubits. So that is, let's say the boundary, it's n over 2, and then it goes up with that.
I'm going to accept that, but I think there is a lot that you didn't tell. But I'm going to accept that, and I think, well, we all know SMART, but if you want to have an introduction, we'll formulate that introduction. Back to you, Sana.
Thank you so much. So I'm afraid we have to move on with the talks. So the next talk will be from one of the supporters of EPIC, and thank you very much for supporting the event today. From VTT, Matteo, Cherchi?
Yeah, Cherchi. Yeah, thank you very much.
Sorry.
Yes, no problem. Thank you very much for the invitation here. So yeah, I will present what we are doing at VTT with quantum computing. It's a very different flavor compared to what we have seen today till now. So it's a different way for photonics to support quantum computing. But let me start to introduce what is VTT. So VTT is a leading research and technology company. It's a state-owned company, so it's a non-profit and limited liability. And we do photonics extensively. We are quite a large organization, but clearly photonics is only a small fraction of that. And we mainly do it in the sites that are in Espoo and Oulu. But so VTT is distributed all over the, let's say, the southern part of Finland. And so we offer both R&D services and contract manufacturing services to companies, and also we participate in European projects and ESA projects and this kind of things. And so the overall turnover, for example, last year it was about 245 million. And yes, that is kind of mainly our. So if you want to learn more, you can visit our website. For example, you can check the annual reports; they are quite nicely done. And when it comes to kind of photonic integration technology, we mainly work in Micronova Fab in Espoo. And we have a fab that is capable to do both R&D and production. And we work, now we are working mainly with 150 millimeter wafer, but in about 2 years, we expect to have a full transition to 200 millimeter. And we have different kind of processes in the same clean room. We can do, as I say, silicon photonics with micron scale waveguides and 0.1 dB per centimeter loss, and integration of germanium photodiodes and many other things. And then we have some processes for MEMS and superconducting devices. Everything is done in the same clean room by our colleagues. And we provide both customized runs and but also MPW runs, especially in photonics, silicon photonics. We offer 2 runs per year that are open, accessible from outside for everyone, with a quite a competitive cost. And yes, we do, as I say, R&D and the production the same place, which is quite unique. Production is limited to some thousand wafers per year, but still it can be meaningful for many applications, especially when it comes to quantum, where it's kind of a high value that counts and not really huge volumes. And as I say, we have this capability of doing silicon photonics, and so we have photonics, also other kind of photonics, MEMS photonics, and the superconducting devices, which can be very interesting for a quantum application, as you can guess. And so, what can we do for you? We have this vision. At VTT, we have been focusing on, like, say, the king at the moment of quantum computers, but it's a superconducting qubit computer. yes, maybe in 10 years this will be turn out to be like the vacuum tube technology, and they will be kind of completely replaced by other technologies. But nowadays is the one that is kind of delivering more, let's say, the one that really was able to demonstrate quantum supremacy, and that is delivering the most promising results when it comes to universal quantum computation. So what we are, since we are not really working on basic research, but we are working on applied research, we want really to help this technology, that, let's say, the most promising nowadays, to scale up. This is a famous picture that Google presented in 2018, where they show that nowadays we are a little bit under 100 qubits, let's say in the 73 range. And you can get some near-term application which are not yet clear. The quantum supremacy demonstrator was done with a completely useless case. But it's for sure, if you really want the universal quantum computer with error correction and everything that is really useful, you have to reach the level of 100,000, 1 million qubit. To do so, you understand that you cannot continue working like nowadays with these cryostats that have, let's say, hundreds of coaxial cables to address each qubit. You cannot really scale it to the 1 million, as you can easily understand. And like you know well the story of telecommunications, when you have some bandwidth problem, you better move to optical means. And this is especially true when you have also the problem of heating. So you don't want to transmit heat inside the cryostat, and the optical fiber is a very nice thermal insulator. So this is really the way to go. And so this is our vision. We want to basically develop optoelectrical and electro-optical interfaces to basically communicate in a cryogenic environment with a quantum processor. And then this is done in our vision using our classical SFQ processor that are kind of superconducting classical logic that can be very fast, 100 gigahertz clock, and very low power consumption. So this is the key, in our opinion, to really communicate with a quantum processor. And you need these optical fibers coming here and then moving the optical signal, fast optical signal, to a fast electrical signal, and vice versa, with very low power consumption and very fast rate, if you want to exploit the. So actually, this our vision has been actually granted very recently FET Open project. We are still actually signing the grant agreement, but basically with our collaborator at Tampere University, with Professor Mircea Ghina, that you will see later on in this event, and then PTB from Germany, Mark Bieles group, Single Quantum, the superconducting nanowire company, and then KTH, Walswiller group, and Professor Leutel group from ETH, and the spin-off from ETH, Polariton. And so, as I say, we have this very large clean room where we can fabricate silicon photonics, integrated silicon photonics, SFQ logic, superconducting qubits, superconducting nanowire single photon detectors, and everything can be done in the same clean room. And we also have capabilities to do 3D integration of all these kind of things. So this is our vision here. And what we want really to follow the same path we have with the silicon photonics. We have now established VTT as one of the leading fabs for silicon photonics, especially when it comes to low-loss silicon photonics. And we want to follow a similar path also for superconducting devices. So we want to establish VTT also as an open, world-class open access foundry for superconducting devices. And in the future, we can also envisage some type of run where we can have both photonics and superconducting elements in the same monolithically integrated. And so we are already actually participating in many quantum initiatives. We are exploiting our, for example, sources from parametric amplifiers we are very famous for, and we are also developing our superconducting qubits, and we are famous for our SFQ logic. And we are also developing our own SNSPDs based on superconducting nanowires. So what can you do for us? What can you do together? I very recently, so 1 week ago, there was this news. It's been also on LinkedIn, as in the VTT website. So we are actually actively now getting a quantum computer for VTT, and there is a call for tender for that. We have this plan to have a kind of innovation partnership. So we want to develop together with some partners the quantum computer, so we can then play with a real machine in-house and do also the interfaces playing with a real machine that is developed in-house. So if you are interested, if you think that you can contribute to this, the tender is open till mid-June, and everybody can see and participate to this tender. And I think, yes, that's it from my side. I hope I stayed in the time slot.
Thank you very much, Matteo. As I already posted in YouTube channel, you have been one of the key people linking silicon photonics and quantum technologies. Your presentation at the meeting at ICFO last year, at the EPIC meeting at ICFO, was fantastic. What have you seen lately on the maturity of silicon photonics for quantum technologies? Anything that making you really, really excited? There are many things that are making me really excited, but I already told them to Martin.
I mean, I think that we have this opportunity to do really this. This is our vision is very different compared to other people, because we are using photonics to serve another technology basically, and we see like an opportunity to do going the same line as this data center power consumption reduction. Is kind of a step further. If you've seen my presentation, I'm talking about the attojoule level of per bit of power consumption. So we are kind of going one step further in the process of power consumption reduction, and it's quite nice because it's kind of going the line along the line of the data center trend in a sense, but pushing the limit to another order of magnitude.
For me, the way that the VTT has been pushing the limit a lot is already for many years working on biosensing, we're working on the data communications, always thinking about the packaging at the same time as developing the structure. I want to introduce the supply chain today. So I'm going to go to Berlin. I'm going to introduce my friend from FineTech. Ralph, thank you very much for joining today.
Hello.
What is FineTech and what are you doing in a meeting on quantum computing?
Yeah, FineTech is a provider of machines. We are very strong in high accuracy machines, high flexible machines. We make fully manual machines on one side and fully automated on the other side. So we are very strong in the field of R&D. And that is why I am here. I want to see what's going on in the quantum computing world. I'm surprised that I know some of the people already, like Amado, who I have met last year, and we are still in a good contact. But also have heard other names and also see other names on the participant list that we work already together. And only from a few of them, I was knowing that they are working for quantum computing. And yeah, I just want to get an overview on who's playing a role in this world, and that's why I'm very glad to be here in the meeting today.
What I'm noticing today, speaking to the many startups in quantum computing developing photonic integrated circuits, that the biggest challenge they have is in packaging. That's clear to me. This is matching all the packaging discussions that we are having in other forums. Are there customers coming to you now thinking, okay, I had this idea for a quantum chip, like the one of QSide or the one like from Hyperonics, how can I package it?
Actually, yes, not really from the companies, at least not to me, because I'm only working for companies in North Germany, north of Europe. So a lot of the companies here are from other parts in the world and in Europe. But actually, there are universities or institutes like the PTB that are asking us, yeah, we have a project there. We want to bond the chip. It is large or very long and so on. And what can we do? Do you have experience with such things? And yeah, it comes more and more. So it's getting a very interesting thing for us.
Well, at Epic, as you have seen, we have focused a lot on the packaging, a lot, because we did realize that the biggest paradigm shift we could do in the design and manufacturing of photonic devices was to teach people to start thinking on packaging. That's why we are so involved with the PICs pilot line. I want to go to the beach. I wanted to go to somewhere close to Bremen, but there's a beach behind you, Alosha. Why is there a beach there?
This is actually in Denmark. So
beautiful.
Was a short break, and I took a picture. And,
so what's QuTech, and what are you doing in this meeting?
Yeah, so QuTech is also a machine manufacturer for packaging in the optical domain. And so QuTech originally comes from fiber connecting technologies. So I think this is quite interesting for people who want to attach fibers to their chips or to their photonic chips, like we're talking about right now.
In the business of quantum technologies, you saw the presentation from Quandela, and they are thinking, oh my God, I have like only a few photons, I have to put them in a photonic integrated circuit. Are we ready there? On the packaging of photonic devices, are we ready there to package quantum devices that cannot lose any single photon?
Yeah, so I mean, what is quite important is that we from QuTech, we like to use like active feedback signals. And we could use, for example, single photon detectors to have the closed loop then available. To have an active alignment to make sure that the fiber is correctly aligned to the waveguides.
And you do fantastic machines. The FineTech and QuTech, they are great machines. And also from Tehema that was mentioned before. But Valérian, are they there yet?
Well, actually, I have to say that I have a lot of documentation from QuTech on my desk, and Silvano from QuTech comes in our lab every month to see where we are, and we are very close to ask you to fabricate a machine, a customized machine for us, because now we are able to do the packaging. So to be continued, actually.
Great, and to be continued in the Epic sign. I love when Epic members work together. I cannot wait any longer. This is the presentation we all have been waiting for. Federico, thank you very much for being with us today. Tell us about IBM. Tell us about the quantum ambassador role that you have. The floor and the attention of everyone is yours.
Thank you very much, Jose. Thank you very much, Sana, and all of you for inviting me this afternoon. I'm very happy to be here and to listen to all of you. So here I am as an IBM Quantum Ambassador. As you maybe know, IBM is investing and is investigating quantum computing since the early 80s, so since quite a long time. Together with us, we have, for example, Charles Bennett, which did the history of quantum computing, and he is already and still working with IBM in Yorktown. As you know, we are focused on superconducting technologies. So let me go to the hardware side, and then I will switch to the software and to the applications. So about the hardware, we are building our chips on superconducting transmons. As soon as we reached a good coherence time, we decided to publish them on the web. So since 2016, IBM quantum chips are available on our website, and all of you can use them and test them. In 2016, we had just a 5 qubits processor, and now we are building much more number processor with a lot of qubits. Now we have 15 qubits for everybody. So all of you can use 5 and 15 qubits on our IBM quantum experience platform. But we have also 20 qubits and 53 qubits processors, which are available for IBM Quantum Network partners, which are enterprises, universities, but also startups that would like to collaborate together with us. As you know, superconducting qubits should work at very low temperatures. So here we see our great fridge that works at 15 millikelvin. But we are not just working on the number of qubits. We have proposed to the community the measurement of quantum volume, which take in consideration not just the number of qubits, but also the coherence time, the crosstalk between qubits, and a lot of our quantities. And from our point of view, it is the best measurement to understand the real power of a quantum processor. We also tried to state a new Morse law. So for the moment, we have doubled the quantum volume each year. So we had a 4 quantum volume processor 4 years ago, and then we have 8, 16, and at the beginning of this year, we presented the 32 quantum volume processor. So we expect the next year to have a 64 quantum volume processor and so on. Also, the Morse law was calculated with just 4 dots, so we hope it could be a good guess. Since the beginning of 2019, we have also announced the first quantum computer for commercial production. So before 2019, we had just a quantum computer inside our research laboratories, which are available, of course, for the community, but are managed by researchers, and so they can, we could switch off them or go in maintenance and so on. Since the beginning of 2019, we are building quantum computers just for external use, which are managed in other places than IBM research sites, places which are specialized for industrial quantum usage and computing usage. So, as I've already said, we are working to scale our processors, but we are also working to mitigate errors and to reduce noise. And that's why these are the topologies on the right of my presentation. These are the topologies of our quantum computers, which are designed to reduce the crosstalk between the qubits. So let's go to the next chart, which is the one regarding the quantum software framework. Since we published our first quantum processor on the web, we had this graphical interface that we can see at the center, in the bottom center of my chart, which is called the Composer. As I've said at the beginning, we had just 5 qubits, so each line represents a qubit, and so it seems like a musical pentagram. And using this graphical tool, it's very easy to begin to work with quantum computing, and we have seen that also several universities and also high schools are beginning their path towards the study of quantum computing and quantum computational languages using this kind of tool. On the left, on the right, we have also an SDK for Python that can be used even on the website or locally. And it enables you to write notebooks which embeds quantum computing codes and recall the processor, which are, of course, on the cloud. So these are 2 ways to program our quantum computers. On the top of my charts, you can see the different components of our software framework, which is Terra, which are the fundaments and the basics of the quantum computing programming. Then Ignis for the reduction of noise, Hair for the simulation, and Aqua, which is one of the first libraries of quantum computing algorithms. All this software framework is designed not to work just with IBM quantum computers, but it can work also with other hardwares, not just superconducting qubits, but also others. For example, at the beginning of this year, we have announced that Alpine Quantum Technologies, which produce ion traps quantum computers, can be programmed using this kind of framework. So I think that it can be used also for other technologies. And this framework is open source, so you can find it on the GitHub and use it there. I will spend my last minutes on the application use case. We are working also on developing application and algorithms for reach the quantum advantage for business and for research. The fields on which we are working on are mainly these four. So process of nature, quantum chemistry and physics, simulation scenarios, for example, for financial, for the economic scenarios, optimization solution, and also for artificial intelligence and machine learning algorithms. These are two initial publications. The yellow one is about quantum chemistry. We use our processor to compute the energy levels of small molecules. And the one in front here, the purple one, is a publication for machine learning usage, in particular quantum support vector machine applications. So I think my timing is okay this way, and of course I'm here to answer your questions.
Thank you so much. Thank you so much for the very nice talk. And EPIC is very application oriented. So it's true, we're all about photonics, but whenever there is possibility of collaboration or building a new, having a new vision about this, you're always welcome to be here. Let me also say that we will have IBM presenting as a keynote at the Quantum Summit in Glasgow. That is EPIC event. I would like to give you the correct name, so everybody now will wait for me. Sorry for that.
The World Quantum Technology Summit, the EPIC World Quantum Technology Summit in September in Glasgow.
Exactly, thank you. You have a question, right?
From the YouTube universe. I never have questions myself, I'm just a speaker.
From YouTube.
So basically, we have a question from Smart Photonics. Say, can we expect to have the 32 qubit computer available to everyone in the next year? Are you also planning to increase the number of 15 qubit computers? Is it just at the moment, is it free at the moment?
So at the moment, the only processors which are free and available are the one of 5 and 15 qubits. The others are restricted to the IBM Quantum Network partners. Our aim is to grow the quantum volume and not just the number of qubits. So as I've already said, of course, it goes together because it's not possible to enlarge the quantum volume without raising the number of qubits. But we have to strongly work also on noise reduction and on the reduction of errors. We hope to double the quantum volume that we have right now of 32. So we hope to double it and to enlarge also the number of qubits. I cannot say today it will be the expectation and the politics of IBM, but I think that we will continue to leave the latest technologies for the quantum network, and I hope that we will be able to use a larger number of qubits on the web in the next years.
There has been a lot of hype, a lot of promises on this quantum computing. I would like to applaud the effort of IBM, and especially the one of the quantum ambassadors, for these 15 qubits that you're giving to the industry, for everyone to test, to play, and to really fully understand that this is not a hype, that this is really the future. And on that, I also would like to introduce you to some friends, and one of them is the company Sony, who is very engaged with EPIC. Actually, we organized a meeting on pixels at Sony last year. It was spectacular. And my friend Klaus Zimmermann is here representing Sony. Klaus, what are you doing here in a quantum computing meeting?
Yes, hello everyone. So my name is Klaus. I'm working as a technology scout at Sony Europe with office in Stuttgart. And as a technology scout, I'm basically interested in all sorts of new technologies that are popping up outside of the Sony universe, and in particular, technologies that we don't develop in-house in an effort maybe to couple these technologies with our own technologies. And so when it comes to quantum computing, we're interested from a component perspective. So we talk about the detectors. Obviously, we have a certain interest in maybe coming up with single photon detectors, ideally working at room temperatures. We're also interested in sources, and of course also at the processor. And then maybe later on down the road, we will look at the system integration. And then of course then it becomes interesting when it's about the commercialization of such a technology. So in general, we are very much a photonic driven company, and this is why we are in particular pursuing and looking at photonic quantum computing, and not so much we're not so much interested in superconducting or ion trapping quantum computers, but of course we look at everything.
It is so hard not to love Klaus when he said that Sony is a photonics-driven company. I'm going to sleep so happy tonight, Klaus. Back to you, Sana.
Thank you so much. And I will go back now to Munich. I have to introduce our friend from Munich, Mess. I hope she did not leave. Here she is.
Oh, not yet. I'm sorry.
Thank you for joining the meeting. How you see it so far?
It's very good, thank you. Of course, I'm from the laser world of photonics. I'm from München, and I'm not a physicist, so it's difficult for me to try to follow. I'm not even saying I'm following, I'm trying to follow. Also to keep my kids busy, that's why I keep a while. But of course, we as the laser world of photonics, we are also thinking of, or we are in the process of trying to find out how we can give the quantum technology in general and also the quantum computing a platform to present themselves. So I would be very happy to get to know a lot of people and to see if we can in next year, June, from the 21st to the 24th, offer you a platform and to give you the chance to present yourself to the rest of the world.
Thank you so much. I think we have a question from QuTech. We are very, very happy to collaborate. QuTech, you have a question?
Yes, actually, I would like to hear something about, I mean, it's more a general question, so nothing specifically specific to the technology, how to produce the PICs. But quantum computing is somehow known as risky for normal computer users in terms of brute force attacks, for example. So how does the safety for, let's say, the normal user is coming along? So how do you see a kind of or possible release for the mainstream market? So if I can buy it, and if everyone can buy it, everyone can do stupid things with quantum computers. So how do you see that? I mean, it's just an open question to anyone. So,
Federico?
Sorry, I didn't understand exactly. You mean the risks of quantum computing regarding, for example, encryption? Are you referring to this topic?
Yeah. Yes, exactly. So encryption and decryption. So since you can do many more calculations with the quantum computer than with the normal computer. So you can just overwhelm a normal system with that.
Just to state, for the moment, our quantum computers can be simulated by classical computers. So for the moment, except for the publication on quantum supremacy, which is a very particular case, we don't have any algorithm that can be executed by a quantum computer and not be executed by a classical one. In any case, we know that, for example, the encryption algorithms can be solved using a quantum computer, for example, using the Peter-Shor algorithm in a very, very short time. On the other side, the Peter-Shor algorithm requires a very large number of qubits, and they should be in a high quality qubits. So if we stay with this kind of qubits that we are producing today, we need a million qubit processor. So we think that the quantum computer that will solve the Peter-Shor algorithm for the large numbers that we use in RSA will arrive in maybe 10 years. Let me say we need 3 or 4 technology steps to reach this kind of machine. So I think that people can stay safe for the next years, but I think that the large enterprises that should grant the privacy of their data should begin today to think about new encryption methods, so post-quantum cryptographic methods.
Thank you so much, Federico. Unfortunately, we have to move on we stay in Munich, but we move to the next talk from my friend Ulrich Eismann. I don't know why I was surprised you're here. I give you the word. Please go ahead.
Do you see my screen?
Yeah, yeah. You can start sharing now. We don't see the share yet.
Okay. It doesn't come up. Hold on a second. I don't know what's going on.
So on the bottom, you have the option share in green. We tried it earlier.
Yeah, I know, but I don't see Zoom at all. I hope my computer doesn't crash right now. That's really weird. That's really weird. And I didn't send you my talk, so.
But I'm sure we can solve this with 2 clicks. So we're going to move to the next speaker, and we'll come back to you afterwards. So let's go to PTV. Let's go to the metrology world. Let's go to the world of optical clocks. Let's go to our new friend, first ever epic presentation, Amado. Thank you very much for joining us this beautiful afternoon. The floor and the attention of everyone goes to the metrology world. The floor is yours. We can see your slides very clearly, but unfortunately we cannot hear you. So I think you might be muted at the moment. I think you need to unmute yourself. I think right now we are fine. We are in business. The floor is yours.
Okay. So can you hear me?
Loud and clear.
Okay, wait a minute. Okay. Sorry. I just made some mistake. Can you hear me still?
We hear you, we see you. We need to see your slides. Click share and we roll.
Yes, sorry.
One of the biggest, the pictures I showed the most last year in my presentations was the optical clock setup from PTV. Let's see if they have it in their slides.
So again, so thanks a lot for being here. It's a very nice pleasure. Unfortunately, I think I will disappoint you because I will not directly speak about optical clocks, which actually is one of the nicest topics here at PTV. But we don't only have also optical clocks at the PTV, but we also have a big effort into building a practical quantum computer. So actually, I am a member of the group led by Professor Christian Ospelkaus. And well, there is a lot of people, of course, involved in this research project, which are listed here. And from my side, I I have about 10 years of experience working with microfabricated ion traps, and I am leading the efforts, as I said, and for developing a practical microwave-driven quantum computer. As what you can see here in this picture, it is an ion trap chip of 5 to 5 millimeter size, which is actually designed, fabricated, and tested here at PTB. So we own our own clean room facilities in which can be done different processes from IC processing till MEMS processing. So on top of this chip, on top of these gold-coated electrodes, we are capable of trapping ions very near to the surface. We trap the ions using electric fields, and we cool the ions using laser beams. And the temperatures we reach with these laser beams are very close to zero temperature. On the other hand, we also have integrated microwave conductors into the chip. And with the help of the field that these integrated microwave conductors produce, and some new scheme that we have developed in the last year, we have been able to demonstrate a state-of-the-art 2-qubit infidelities in the range of 10 to the minus 3. So let me go to the next slide. Okay. So our quantum computer approach, as I was mentioning you, it's based on trapped ions. So very shortly, technically this is achieved using a near field approach, which means we bring the qubits, which in our case are beryllium ions, very close to tiny embedded conductors in the trap, which operate at the 1 gigahertz range. And these conductors produce a magnetic field pattern, which allow us to manipulate the internal state of the qubits. So that the potential which we have in the trap allow us to conduct, so to say, the information between one qubit to the other one. It means it works as a quantum bus. And so then these allow us to perform logic operations or quantum gates. In contrast to the more standard laser-based approach, this mechanism allows us to embed directly the gate register, so to say, into a scalable microstructure. And so what we can offer actually to potential partners is our expertise and state-of-the-art microwave quantum computing with trapped ions. So our group is currently among the leading groups worldwide towards the practical realization of a microwave-driven quantum computer. And also our group is a part of a related European quantum technology flagship project called MicroQC, which also pursues as a main goal to achieve a practical microwave-driven quantum computer. So we have we work with different collaborators all among Europe, and we strengthen on our technologies, which is the microwave approach and the microfabrication of ion traps. So, as I mentioned, we have developed a method which allows us to be able of realizing these logic operations even under noise environments. So that this with this method we are capable of reaching infidelities of the 10 to the minus 3, which are at least till now a state of the art on the microwave quantum approach. So on the other side, we also offer to potential partners state-of-the-art ion trapping devices and fabrication technologies. So we have recently patented a multi-layer ion trap technology, which not only offers us high-performance devices, but it also offers us a practical way to for hybrid integration of other also important components, such as microelectronics or micro-optics, among others. So that our approach allows us the implementation of complex multi-registers. So for example, we want to manipulate a large number of qubits, so then we can define dedicated zones for manipulation, for storage, and for readout. So now coming to what we actually need from potential partners. As we have seen in many discussions here, and I think is the main topic of today, we are also interested on integration. This is a very key step towards moving to a different stage of our research, and integration it's needed. Mostly what is needed is to integrate the most promising approaches so far independently demonstrated. And this integration is the present challenge in our research. So what we are actually looking for from potential partners is a strong collaboration, which should allow us to build our expertise of integrated quantum logic gates, trap operation, and microtrap fabrication into a more scalable device in which we could able to manipulate a large number of qubits. And this device hopefully will have even higher fidelities that we have demonstrated so far, and reach the fault-tolerant operation regime. So some of the future challenges are depicted in this picture I'm showing here on the right. And some of the challenges we would like to address is, for instance, if we might require integrating low noise control electronics, or also integrating, for instance, optical guides, waveguides, or also suitable single photon detectors. So our hope is that if most of these challenges are successfully addressed, our current technology could be a scale for the realization of a quantum computer demonstrator with up to 100 qubits. And so this reaching this demonstrator at the moment doesn't pose major technological challenges to what we have. So it means, in principle, we don't need major disruptive technological changes. And I think with this last part, I would like to thank for having the opportunity to present our research to you. Thank
Fantastic, Amado. It's your first ever EPIC meeting, and you already know the EPIC lemma, which is, what can you do for them, or can they do for you? These are my challenges, and you were very clear on them. In this meeting, what we want to do is to find you people who can help you with these challenges. So I'm going to go first to the silicon nitride manufacturing of Lyonics, a beautiful company in Enschede, in a beautiful city in the Netherlands, where I am as well. Thank you very much for joining today. He's looking for UV waveguides. Can you help him with that?
What waveguides?
UV.
Oh, UV. I believe that's just beyond our spec. I mean, Caterina lovely explained it. Our transparency range goes, typically up to 400 nanometers, so not much below that.
Yeah. This is not only a challenge in our field, right? This is like a general challenge to go below 400 nanometers. Yeah.
Yes.
We have been working with different entities to actually develop platforms for the UV, actually for lithography applications. So there is still some room to grow there. I don't know if AMO, if Anna Lena would like to comment on this, on waveguides for very low wavelengths, for short wavelengths.
Yeah, basically we are there on the same page as Lyonics. So we're also using silicon nitride, which then, I mean, above 400 nanometer, it might work pretty good, but below so far, no experience there. But definitely, I mean, we are open to also dive into new material systems in the future. So if you have some ideas, of course.
Yeah, well, we are actually planning to use atomic layer deposition of alumina films because there are some reports which show that is a nice material, at least for the wavelength we are looking for, which are close to 400 nanometers, not to.
Amado, I'm not going to stop until I find it. I'm going to go now to Finland because I know they are really great ones when it comes to new layer stacks. And I have discussed with Mirisha about UV in a different context. Mirisha, do you think there is something we can do to help making some waveguides in the UV?
So, Jose, it's a question you want. I had a question, actually, a bit different question than the UV waveguides. So let me. Well, I think that it's a bit of out of what I can answer now. But I was just wondering. Very nice talk, by the way. So, what kind of lasers are you using for trapping and manipulating beryllium?
Oh well, we use the 313 nanometer, which is some frequency from 1550 nanometers. So it's twice some.
So and these are fiber lasers or solid state lasers?
Yes, these are fiber lasers. Yes.
Yeah. So well, maybe you bear with me to the end then, and you will see maybe a bit better opportunity. Thank you.
Okay, so we can talk more later on. I think that's really nice.
Fantastic. I actually, when I was talking to Lena about AMO, I know that they've been working very heavily on introducing graphene detectors. PTV is looking for highly integrated single photon detectors. Anything that you've been doing, or maybe any room for collaboration there?
So from my point of view, I don't see graphene as an alternative approach for single photon detectors, but maybe there's a hybrid integration possible of having also single photon detectors at higher temperatures than the niobium nitride ones. So definitely that's one research route we want to go in the next couple of years. So let's see.
They are open for this kind of research collaboration. So you already have there two challenges, the UV waveguides, which I think still is possible, and the detectors. I'm going to go to one of our members, key member, Aurea Technology in the field of quantum. This is new companies that joined EPIC when quantum was becoming an important part of EPIC. What do you think of the meeting so far? What kind of cooperations would you like to do after the meeting? And what is Aurea?
Hello everyone, thank you, Jose, for giving me the word. So at Aurea Technology, we develop, manufacture, entangled photon sources and photon detectors. So we are not at the same scale of integrated photonics because we're more on tabletops module, let's say. But as of today, we're working closely to new companies who are willing to develop new calculation and manipulation systems like the QUIX, for example, which was a good example of such system which will be compatible with our, let's say, detectors and sources. So far, the type of collaboration we are looking for is more to interface and try to interface our instruments with these new techniques of manipulation of photons for quantum computing, but also for communication and quantum cryptography. So far, I see that some companies may be interesting for future projects. So right now, I don't have a clear idea of what is feasible, but I'm sure that some collaboration could be.
There's a lot still to come, and we still have 33 minutes to push for that. And I'm going to go to Edinburgh. I'm going to go to the company Chroma City, which is one of my favorite laser suppliers at EPIC. Thank you very much for joining us today. The floor and the attention of everyone goes to Scotland.
Hello, thank you very much indeed. It won't allow me to share my screen. Hang on a
Is
moment.
the button the green one with the little arrow that points up?
Yep.
I think we may have lost you. No problem at all. We go to Toptica because now I heard the presentation is ready, right, Ulrich? Now everything is solved and now you can share your screen. So Ulrich, thank you very much for being with us today. The floor and the attention of everyone goes to Munich.
Yeah, welcome back to Munich. Do you see my screen?
Not yet. As soon as you press the green button, we'll be ready to rock.
Again, it doesn't work. No way. Come on.
This is the beauty of the live world in
That's
which,
the beauty of the live
everything
world.
was supposed to be working.
Do you see my screen now? We tried it before.
That's why it's important to send all the presentations to
No,
share.
Oh, no worries.
No, because we stay in the field of lasers, but now we stay also in Scotland, but we go to the other side. We go to Glasgow and we go to Unique Laser. Thank you very much for joining us today. I really know that the lasers from Unique will work when we share the screen. Thank you very much. The floor and the attention of everyone is to Mark Mackenzie. Yes. Or maybe, yes, excellent. The floor, we see it crystal clear. The floor is yours. But we cannot hear you. So it's a beautiful day. A beautiful, beautiful.
Can you hear me now?
Yes, now, perfect. The floor is yours.
Thank you, I was muted. Slight correction first, we're in Edinburgh, not Glasgow. So we're actually only a few miles away from Chromasity. We're very close to each other. We are a manufacturer of single frequency lasers. We make these in the UV to near IR wavelengths. And I'll just briefly cover how we do that, our BRAMS technology, what we're doing in the quantum photonics field, and what we're looking for from other companies at this meeting today. So BRAMS technology is Bragg range mix and mode selector. I've got a diagram of this here. This is a component which can be dropped into a range of different laser cavity designs, works at all wavelengths. And the component itself is made up of a mix interferometer and a volume Bragg rating. So each of these are frequency selective elements, and combined together, they enable us to achieve single frequency in the system. There's many ways of achieving single frequencies in lasers. The reason we use this method is that it's very small, it's very compact, which gives it good inherent thermomechanical stability, which is beneficial for the system. We combine that with a piezoelectric transducer for feedback in one of the arms and frequency locking in order to maintain long-term stability. The method we use for that is called tilt locking. I won't cover that today, but it's quite a widely used technique. There we go. The way these components work together is shown in the model here on the right, where we have the transmission of the VBG in red and the transmission of the mixin in black. So you can see there's many different transmission peaks in the mixin, and by changing the arm length of this, we can tune it so there's only one peak within the VBG. Combined effect being to limit the longitudinal modes the laser can work on to only a single one with the lowest loss per round trip. The results of this in a real system are shown at the bottom, where we have a 1064 nanometer laser operating on single frequency. You can see zoomed in, it is a true single frequency. And we have the long-term stability in the bottom right, including the warm-up time and thermal stabilization at the beginning there. So this is what we do for all our systems. And at the moment, we're trying to expand our range of lasers into the quantum photonics market. We've been doing a number of projects in this on 689, 698.4, 780.24, 813, and this is targeting strontium and rubidium atoms. All these projects have been funded by UKRI, and they're looking at various things such as miniaturization, stability, portability, power scaling. The biggest ongoing project we have at the moment is called Gravity Pioneer, which is looking to develop a quantum gravity sensor which can compete with more traditional non-quantum based solutions. And for that, we're developing a 780.24 system. There's many challenges from us as a manufacturer in making these lasers for this application, which don't necessarily apply to others. Typically, the quantum market wants lower line widths, actually higher powers than what is easy to produce at present. And they want the robustness potentially to move these systems about. For the gravity project especially, they're looking to take this system, put it in a box, take this box into a field and have it work. So we're going to be doing environmental testing as part of that, including things like shaking the system to see how it behaves. Initial results of this are shown here, where we have a 70 milliwatt system on the right, single frequency, and the stability over time is 60 femtometers over 12 hours. That's our previous system. The one we are building now will hopefully improve on all these things. So we're looking at ways of improving the stability, improving the power, and also increasing the robustness and lowering the line width. So everything, essentially. Things we are interested in is most of our projects at the moment have been in this Gravity Pioneer and with Fraunhofer looking at various things. But what we'd be quite interested in is broadening our scope into the quantum computing sector if possible. We'd be interested in trialing our systems with anyone who can potentially make use of them and giving us feedback of is it suitable for you? Why not? And how it can be improved. We are also interested in partnering with anyone who can potentially be a supplier of very robust and stable components, ideally very small components as well, and who can do work on locking. I mentioned tilt locking before, that's our current locking method, but we're interested in broadening that to other methods such as gas cell, reference locking, and other methods. So if anyone's interested in any of that, please contact me and we can discuss that. Thank you.
Thank you so much for the nice presentations. So there's here a possibility, business opportunity that we see. Do you have questions before we move on to the next talk? Because unfortunately we're tight on time, so I would like to try again with you, Ulrich. Can we try to have the presentation?
Yes.
Thank you. Okay.
With any luck this time.
So here I am.
Ulrich with the. Oh, we have. Who shared now?
So am I next?
Can you try Toptica? Can you try to share first?
Yeah, I can try to share, but
okay.
I just sent the slides over. So if it doesn't work,
okay.
please come up with these slides.
I think it's working now.
Is it working? Do you see the Epic website?
I see the Epic website.
Awesome.
Good sign.
All right.
Excellent. Just
here we
presentation.
are. You see my presentation?
Yeah.
I cannot believe it.
Sorry, Christopher. I kind of kept the old order, but I hope that's okay.
Good things come in three. That's what they say in English. All right. So let's get started. I don't have much time. So Qt Flagship and Beyond, that's the title of my talk. I'm going to tell you a little bit about what Toptica is doing in the quantum technologies in general, but also a little bit more in detail what we are doing for quantum computing. So let me give you a brief introduction about the company. So key figures here, we are about a little bit more than 300 people right now, a little bit more than 70 million euros turnover, and a little bit older than 20 years. We built diode laser systems from the very beginning of the company. We cover basically a very large range of wavelengths with these lasers, so 190 to 4,000 nanometers. Since almost the beginning of the foundation of the company, we also built ultra-fast picosecond, femtosecond fiber lasers, covering a wide range from 488 to 2,200 nanometers and also from 5 to 15 microns. In some sense, if you combine these two technologies, you end up building frequency combs. So these cover also 420 to 2,200 nanometers. And we also build terahertz systems spanning from 0.1 to 6 terahertz. This kind of technology range allows us to build products which we think of as quantum shovels, depicted here, because they are essentially tools which you can use to build your own quantum application. And of course, as you can see here, we claim to do this at all wavelengths. And how does it look in practice? Well, if you focus on the diode lasers, then you can see the emission spectrum here. I don't want you to look at the very details of this map, but maybe take into consideration that we start at the very low frequencies here with basically the milliwatt class lasers. But even in the UV, we go up to watt class lasers very soon, and up here in the visible, always providing something like a watt, and this extends all the way out to 4 micrometers. That whole laser range is now digitally controlled, as you can see here, our digital laser controller, which allows to control these lasers from far away, to lock them in frequency, to something to switch them to different powers, and so on and so forth. So many things are possible with this new kind of digital control. I told you we also built frequency combs. Well, this is how they look. Essentially, you end up with a box like this. It's all fiber-based. You have extension units to go to different output wavelengths, and so on and so forth. You also have a nice and convenient software package which comes with it. Here you can see some beat signals with some CW lasers. So that's all pretty neat. Technologically, this is advantages that you don't have a CEO frequency. So this is basically offset frequency free. We call this zero technology. Again, wavelength coverage 420 to 2200 nanometers and remote and convenient. Now, all these lasers usually go into labs, which, well, many of you have seen before, I guess. They look like this. And most of the people think this is very, very beautiful. And well, you can find this very beautiful. And I come from this kind of lab also. It's, first of all, it's a lot of work to set this all up and make it running. But I think many people, especially from the industry, they quickly get a grasp saying, well, this cannot be the future if you want to run these systems, if you want to scale these up, if you want them to run them continuously, and so on and so forth. And in some sense, we made the next step at Toptica, and we call this step the laser rack systems, because we have taken the lasers I have presented to you before, so essentially the frequency combs, or the external cavity diode lasers, frequency doubled lasers also, and amplified lasers, and we have put them into, well, more or less standard industry grade 19-inch racks. So what you end up with is, well, a rack mountable diode laser module and frequency comb modules, of course. You cover almost the full range, basically limited by the fibers. And this is a subject which came up again and again in this session. So basically we start at 330 and go all the way up to 1625 nanometers. All that stuff is extensively tested and qualified because we want to make sure you get the same, if not better performance when you move from the optical table to the rack system. And as with the optical table system, everything is convenient, remote control, frequency locking is established. So all in all, this boils down to, well, to the fact that we can offer complete quantum technology solutions which come in a rack. And to show you that we can also integrate this even further, we took part, or even we led the consortium of the Optical project, which was done together also with PTB, with many other partners from university and from also from the industry. Everything was funded by the German Federal Ministry of Education and Research. And what you can see is that in basically two of this kind of racks, you integrate all the optics, all the electronics, all the physics package it takes to run a single ytterbium ion atomic clock. So that is pretty neat, I find. And well, if you think of ion clocks, some of you might know that, well, having an ion clock is not so far from having a quantum computer based on ions. And we want to talk about quantum computing in this session. But first of all, let me give you an overview of more quantum technology activities we do at Toptica. So the quantum flagship is basically well, separated in 4 pillars. And we are very proud to be part of projects in each of these pillars. So for instance, we're part of the Quantum Internet Alliance, which does quantum communication. We are part of Action, and I will come to this in a second, which does computation. We are part of Pasquans, which is doing simulation, quantum simulation. And we're also part of IQ Clock, which is part of the sensing and metrology pillar. I will now concentrate on Action. As you can guess from the name already, well, it's based on atoms. So the project is about advanced quantum computing with trapped ions. And I only have a little bit of time left, so I can show you the status of how the system looks right now. Here you can see a few people, especially Thomas Mons, who is the project leader of the whole collaboration. They're standing in front of the system, and as I told you, it looks very much like the Optical. You have again 2 racks, who, by the way, look very similar to the Toptica racks. On the left, you basically have the laser system, and here you see the Toptica laser, many more control electronics. On the right-hand side, you have the physics package. And inside of that package, you can see the zoom out here sits the vacuum chamber with the ion trap. And inside the ion trap, people have trapped already linear chains of something like 50 ions. And each of this ion, of course, can then serve as a qubit for quantum computation. So if you want to know more about the project, please go to the website www.action.eu. And with this, I want to thank you.
And I want to thank you for a great presentation and for really always looking for this kind of collaboration. So let's start some collaborations. Let's do the epic question. What can you do for them? What can they do for you?
Well, as a laser manufacturer, I would say that many of the times we look into components, of course. So whenever there are better components, say better crystals for nonlinear optics or better optical semiconductors, we are pretty happy. On the other hand, I showed you we do kind of system integration right now already. And if you think this a little bit further, it of course may also be interesting to look into PIC technology, as we have talked about a lot in this session already.
Fantastic. Let me introduce you to a potential collaborator. One of our EPIC members is Helia Photonics. They are in Scotland. They make fantastic coding for optics. Helia is very involved in the quantum world. Like everybody in Scotland is perhaps the biggest ecosystem there in quantum. I would like to thank you very much for being at the meeting today. What kind of collaboration would you like to start, and what can you do for them, and what can they do for you? I think we have you muted, and I'm trying to unmute you. It doesn't work. This is today the day of IT, I think. We're going to call it the day of IT on the quantum technologies. I think she's nodding along. That's okay. Another EPIC member who I think would be interesting for you to discuss and collaborate is the member Excelitas. Excelitas, when it comes to components, is one of the main suppliers that we have in EPIC. Thank you very much. I'm going to try, because you never know with this dive meeting today. I promise the other ones have worked perfectly. I'm going to try with EPIC member Excelitas. It's great. It's working great. Thank you very much for joining the meeting on quantum computing. What have you learned so far? What kind of collaborations would you like to do after this?
It's been very interesting. Thank you. Sorry, I've not been on video, but I'm not allowed to use Zoom on my work stuff, so I'm using my tablet, and it sits
We will not tell anyone.
Normally. But I know how to use my private thing here. No, this is really interesting. Obviously, a lot of the work here is outside the area that we support with our single photon counting modules, but I'm certainly very keen to to make contact where it's relevant. I've just been taking notes quietly in the background.
Fantastic. And I think we now go to the last laser manufacturer, to the last but one laser manufacturer today. We go to Chroma City and then to Vexlum. Chroma City, thank you very much. Now going back to a few meters away from UniK in Edinburgh, the floor and the attention of everyone. Look, see how well it works. It's yours, Christopher.
There you are, finally at last. Thank you very much, Jose. Thank you for inviting us along as well. And I hope everyone is safe and well. A bit of background about Chromacity. I am one of the co-founders of the organization. We founded the company just over 7 years ago, originally to develop laser sources for life sciences imaging, but over time we have diversified. So I'll just run you briefly through the types of technologies that we've developed. It all originally developed around the fixed wavelength 1 micron laser source that we developed in the very early days. Originally, this was a system that delivered about 0.5 watt. We've now got a system that delivers 4 watts, if not more. And we've used that capability and that efficient, we've got a very efficient laser process. We've used that laser efficiency to then drive a number of fixed wavelength laser sources into the visible, and also we have a 350 nanometer source. But we've also used it to drive an optical parametric oscillator. In fact, a number of optical parametric oscillators that allow us to generate light anywhere from 1.45 microns all the way up to 12 microns with varying degrees of high brightness pulse durations. We try and make these systems as compact as possible. We don't have any systems that require water cooling, therefore you don't need any kind of additional infrastructure. And we've tried to make these systems as affordable as possible. And as I said, we've diversified our capabilities over the years. We were looking at multi-photon and 2-photon SHG microscopy in the early days. We're now looking at much more complex things, particularly in spectroscopy, but we've also done some significant work in the world of quantum optics and quantum technologies. And while we haven't specifically been involved in quantum computing applications, we have been involved in quantum key distribution, particularly with academics at Glasgow University. And the work that I'd like to just briefly cover here today, I think is important because we've been able to use both our fixed and tunable wavelength laser sources as part of this body of work, which has been really exciting for us. This work here stems from the need and want to look at quantum key distribution, not just at the short wavelength regions, but also moving at longer wavelength regions where there's less blackbody radiation, so beyond the sort of telecoms wavelengths. And so the academics that we've been working with, particularly led by Matteo at Glasgow University, is looking at identifying atmospheric windows at the longer wavelengths to generate quantum entangled photon pairs at 2 microns. And this is for sort of like ground to satellite based communications. And there are a number of challenges in this work. One is the polarization maintaining fibers at 2 microns, but also looking for high efficiency single photon detectors. And the work that he's been doing is using our 1 micron source to pump piplin to generate photon pairs at 2 microns, pass those photons into a Honger-Mandel interferometer to generate visibilities of greater than 88%, demonstrating the indistinguishability between these photon pairs, which is absolutely fantastic. But he's been working in collaboration with Professor Robert Hadfield as well, who is developing more and more efficient semiconductor nanowire single photon detectors. And he's been using our OPO, our broad bandwidth OPO technologies, in order to interrogate these devices and really understand what's going on in the development of these single photon detectors, to the point where we can now carry out this kind of research. And this is the first work that's been developed at 2 microns and was recently published in Science Advances. So for us, it's been a really, really exciting project. It's something that we want to get more involved in. And I guess our ask is, is there anyone else out there who wants to do really interesting science with us? We have other systems out there doing quantum optics experiments. We've developed the capability of generating entangled photon pairs in the visible using our third harmonic system. And we also have a number of customers who are looking at interrogating silicon nitride devices at odd wavelengths beyond the telecoms wavelengths with our OPOs. So we have a suite of capabilities, and we'd be interested in having conversations with people who want to benefit from these highly efficient and relatively low cost laser systems. So with that, I'd like to say thank you for this opportunity, and I'll pass it back to you, Jose.
Thank you so much. I will take it from here. Thank you so much for the very nice talk. Thank you for being open to all kinds of collaborations. I would like to see if somebody have a question to you from the audience before. If not, I would like to introduce our friend here from the University of Stuttgart, Mr. Manfred. How are you doing?
So, my name is Manfred Bird. I'm a professor at the University of Stuttgart, and some of the people here might know me, for example, from HHI, Mr. Schell, and other. We are doing research in the area of photonic integrated circuits, and we have been quite successful doing very high efficient coupling, grating couplers with backside mirror to the waveguides. And we also have devices like detectors, multimode interference filters, which have been used especially for telecom applications. But there might be a new use of those devices in the quantum computing area.
Thank you so much for joining the meeting today, and we're looking forward to have these big collaborations, particularly with PICs. I remind you that EPIC take part in PICs up the pilot line, and if you would like to know more about it, you can reach out to me or to my colleague Ana Gonzalez. Now we're so much looking forward to the laser sources that you promised us, Merke, from Wixlum. We are really looking forward to see your
okay, great.
lasers.
So
they are unmuted. Yeah.
Can you hear me?
Yes. Now we want to see the lasers you promised our guests.
Let me see. Great. So let me see. Are you seeing the slide?
Not yet.
Okay.
Oh, now. Yeah. Good.
Okay, great. So I'm Mircea Guina. I'm from Tampere, affiliated with Wixlum. Great, Jose, for inviting us here. And of course, great for acknowledging that Wixlum, it is in the area of sources for quantum technology. It is our market entry, and I'm very happy to introduce our technology platform for many other applications too. So Wixlum has been founded in 2017. We are located in Tampere, so obviously it's a spin-off from Tampere University Optoelectronics Research Center. So our legacy, it stays in semiconductor technology, and we have full access to processes from the design to laser assembly. And this is a core technology then used for VCSELs. So VCSELs are a new type of sources. I will briefly tell a little bit what those are, because there may be interesting features for other applications. But well, in general, so they try to solve many of the issues what we have in general in application, from high brightness to compactness to price and a few other features which are relevant for quantum technology application, like narrow line with stability, low noise. We are addressing quantum technology as our entry market, but the platform would be offering also interesting opportunities for industrial application, for medical applications. So hopefully we'll see Wixlum to future workshop of EPIC. We have several product lines. So we are starting from the gain mirrors, like the smallest type or the lowest development effort in terms of VCSELs, just to get the gain mirrors, and we provide those to scientific communities which wants to do themselves the lasers and develop new application. But what you will see now in this talk, you will see more what we have done for high power, watt level, single frequency lasers. Okay, I promised to introduce you a little bit what the VCSEL is. So we are developing, well, lasers are 60 years old, yes. So, and there is always new, and there is always a new way to make the lasers more appealing to application. And basically, this is what VCSEL is trying to bridge. It's a vertical external cavity surface emitting laser. Again, it's a bit similar to what you see, most of you know VCSELs, only that, let's say it has an external cavity. So it has a disk laser architecture. with a core which is not a solid state, what you will see in the traditional SINDIS lasers, but a semiconductor. So you see here this small chip, so millimeter by millimeter. That is the heart of a VCSEL, which is optically pumped. Typically can be electrically, but we use it to optically pump for many reasons. One of the main reason being also the high power. So by scaling the pump beam on this mirror, we can get a lot of power. How much power? 100 watts even. Typically watt level to 10 watt level with fundamental transverse mode beam. And well, if Jose would be in my place now, he will say, this is amazing lasers. So it's an amazing, probably would be amazing versatility in terms of wavelengths. This type of lasers have covered from UV to 4 and 5 micrometers. And with the same, again, with similar architectures. Compared to solid-state lasers, they are very simple to pump because they are wavelengths insensitive or very little sensitivity in terms of what pump wavelengths we are using. So getting back to a little bit bridging to quantum technology. So they have a feature that we can use intracavity element to initiate single frequency operation. But they also have this external cavity with extremely high Q and without relaxation oscillation. So it's a very low noise compared to traditional solid state semiconductor lasers. And well, in addition, one can use also intracavity second harmonic generation for getting more wavelength versatility than the semiconductor itself gives. And well, I bridge very fast with where these lasers are used in the quantum technology. So they are already used by some labs, and we want to see more using them in the quantum information processing using trapped ions and neutral atoms. These are the flavor of the quantum computing or quantum information processing, where the state are well reproducible, where you have seen you can get already quite a few ions already trapped, and you can manipulate them. But you have also seen today that actually they are pretty demanding in terms of laser requirements, and it's not just the wavelength. There is a line noise, and there is a noise and tunability and polarization stability, pointing stability, makes the labs looking more like what you have seen in Toptica. And then, by the way, so if you have just follow Cleo presentation on quantum technology last week, it was an interesting presentation from Hanwell presenting their computer with ion trapping, and they made a very clear statement. They use 10 plus wavelengths and 20 plus frequency tones. And this puts a lot of need in terms of, first of all, making the lasers more affordable, enabling modularity. But then also in terms of having the lasers to enable use of maybe more favorable ions, more favorable atoms. Often the ion trapping and neutral atoms communities, research communities, they choose ions or atoms based on the laser available. It doesn't need to be like this. You need to choose it based on what you want to do. There is a little bit of different application what we see VCSEL used also in the resonant excitation of solid state quantum dot system like indium arsenide and so on. I am not touching that. Well, basically, to put this in a perspective of what we can cover in wavelength versatility with high brightness, high power, watt level, single frequency is basically seen in this table. So with the red is a fundamental operation wavelengths, what we can get straight from the materials. With the green, a second harmonic generation, we can have third harmonic generation, we can have fourth harmonic generation. There are many ions, or actually all ions and atoms what one would think about. We have particularly focused on magnesium and beryllium, what we have seen from our friend at PTB. So let me just show a state-of-the-art experiment with beryllium ions. This is a paper, what you will find it in arXiv. This is a full demonstration of ion trapping and manipulating with Vexel-based systems. So we needed to generate 235 nanometers light for photoionization, and we needed to generate 330 nanometer light for cooling. And we started this with fundamental operation at 940 nanometers and 1252 nanometers. And you see here we got pretty broad tuning. First of all, it's 10 terahertz, so we talk about tens of nanometers tuning, but we also got a lot of power and a single frequency operation. And I'm not going in detail. I'm just saying that if you are interested to see this first experiment with a beryllium ion trapping, fully based on Vexel, watch for this paper, and then you will see also other the power what we achieve in UV and how the implementation was done. Close to last slide. So this is how our systems are looking now. So this is a shoe box size. So 30 centimeters by 16 by 10, with all the pumps inside and turnkey systems. We cover these wavelengths in the 910, 1260, and then the 2 micrometers we could cover in between rather easy. Currently, we focus on 700 and 910 nanometer range for fundamental. And again, we reach watt level power with single frequency operation and broad tunability. The highest power we have in the lab for single frequency, it is 16 watt. You see this curve here on the right, the output power. And we have also obtained watt level in second harmonic generation going to visible and UV. Of course, Jose, you are right. For this, we need UV. So we should have hundreds of milliwatts in UV with these nice features of low noise and single frequency. And that is where we are now. Take a look on our website. You will see a lot more. I just anticipated your question. So let me just straight, in the interest of time, go to it. So what I would like to see, first of all, I'm very happy to see PTB here. Of course, very happy to see other companies like Toptica and the others. I would like to see more of the ion trapping and neutral atoms quantum research community. It is a lot better form in US, seems to be a lot less form as part of EPIC or interaction with EPIC. There are tens of groups in Europe which could collaborate with us, or we could help them. And I think that would be great to see them more at these meetings. Of course, we like to identify, or EPIC could help to identify us more partnership with people moving in building quantum technology, quantum computers using ion trapping or neutral atoms. And of course, for this application and other application, we also have need in complementary expertise on the value chain, from, I don't know, laser stabilization, electronics, low noise pumps, and so on. Thank you very much.
Thank you very much, Mirisha. You know me very well. Basically, you know me for 20 years, so of course you know me very well. And you know that I'm amazed by what you're doing now, amazed how you want to bring the Vexels very close to match the unmet need in UV lasers for the quantum technologies. There's, of course, a lot of interest for you. One of your potential future collaborators is the foundry in Singapore, A-Star. So my friend Leonid Krivitsky is wondering, how significant is the amplified spontaneous emission in the Vexels?
Wow, that's a great question. So I like physics. So there is no amplified spontaneous emission in the Vexels. And the reason is that we talk about high Q cavity lasers. The output, it's 1%, 2% the output coupler. So the Q it's in the range of million. Therefore, we operate in an extremely high saturation regime. There is no AC in a VCSEL, and this is one very important in terms of noise properties. The other properties that the VCSELs are type class A lasers. There are no relaxation oscillation. Basically, the photon lifetime is longer than the gain recovery. So another way why VCSELs are very low noise sources.
I think you are in the money. I think you are in business. I think soon you're going to have a lot of Teslas parked outside. I want these VCSELs to be everywhere, deployed everywhere. So I have a member, AMS Technologies. Thank you very much for joining this meeting. What did you learn so far? And how can we help Vexlum deploy these VCSELs everywhere for quantum technologies?
It's a very interesting technology. For me, it's pretty new. So I have to say I learned a lot today, but I need to look more into it to get closer to that technology.
And the final question that we have is not just for you, it's for everyone. I got the question in the beginning, and I've been waiting to ask until the end, because now we have covered the lasers, the detectors, the photonic integrated circuits, everything. Let's answer the question. We have a question from Giesz, from Helia Photonics, in Torbay. And he's wondering, does anyone have an opinion where the operating temperatures for quantum computing components in the near future and the implications for packaging? And for me, this is really the big unknown today. So I want to start with the laser part, and I think Mirsha there, you have to take the lead. You are working in many quantum projects. What is the need that you are seeing in temperature stabilization and temperature operation?
Hello. So do you want me to?
Yes.
Well, of course. I mean, there are many. So first of all, VCSELs they get to these high power levels because we do very good thermal management. The laser, what you have seen that we have, it operates at room temperature, but the gain chip inside is very important for that. And that is a key technology, thermal management, and this is why we are able to make now not just research. We have done that for 15 years. Probably you have visited our group when we were just starting. So it's there is always need for better solution, for actually to handle better the power density, and then, well, there are other ways to handle with temperature behavior. It's like not generating heat, and there is this is another way how we work with different materials to reduce the heat generation in terms of laser operation. And in photonic integration, again, I don't want to steal here the show, but we are doing quite a few things on new materials which do not generate heat.
It is, of course, the biggest challenge that we have, and it is not only a material challenge, a packaging challenge, it's actually a bit of both. In the material side, there is, I have to say, honestly, and because I know you for 20 years, there is no better MBE growth in Europe that they want it on in Tampere.
Oh, thank
honestly,
you.
I have to say it.
Thank you.
And you can quote me on this, I'm live. But on the packaging, do you have this solved? Are you looking for collaborations, for partnerships?
Yeah, sure. I mean, I think that it's well, we know quite a few friends here, and it's great that photonic integration is making big moves here. So first of all, if these lasers, including our lasers, or any new laser technology has to come to make a big impact, we need to learn to package things with using automated tools. And we are actually part with QuTech from automated tools, which may be suitable for these more complex systems. And that is certainly packaging. It's extremely important. It is not universal in the photonics. We also, all of us know this. So we really need to build the ecosystem and understanding how do we make tools which are versatile and faster coming to support the laser from research to production.
needless to say, we'd like to remind you that they are looking for packaging collaboration. So anybody who would like to interact with any of the participants today, just send me an email. There's a lot of cooperations there. I would like to give the final word to my favorite packaging company, which is Icon Photonics. And what did you learn today? How can you help these companies? What kind of cooperations would you like to do afterwards, Carlos?
Yes, well, again, we deal with fiber coupling and packaging. We try to bring a solution for helping these issues in terms of bringing a passive solution, a collaborative manufacturing solution. How we do this? We do with the polymer-based technology that we had on the chip. We bring optics to the chip at the wafer level. So we bring somehow micro-optics, micro-technologies process, micro-technologies for collective manufacturing. I learned here there is some challenge on packaging, mainly about the temperature. We must work at the cryogenic temperature, so the packaging must also operate on these temperatures. Every photon is important, so coupling must be really high efficient. So I think we can bring a solution today, even though we focus on datacom transceivers. But I think we can also contribute on the quantum. So we are open to collaborate and open to receive any challenge from all of these partners of this meeting.
The presentation from Carlos in the previous meeting can be seen in YouTube. It's actually quite spectacular how they can package pixels. And I think there should be a way that I introduce you to Vexlum and to the other partners today. For me, it was a great meeting. Today I really learned a lot. Learned a lot in terms of the challenges that we are having in the quantum business. And while I was chatting with you in WhatsApp, I did a lot of that. And when I was chatting in the YouTube channel, when I was interacting with many people, I also took a few notes. For me, when it comes to the photonics, we had different building blocks. One of them is the laser, and you actually see a huge market growing here. Toptica, Unikey, Chroma City, they really show that this is something very interesting for them. It used to be like an R&D time, but now it's a real business. And there was a challenge on PTV, and I think the way to go into integrated miniaturized systems is the VCSELs, and I'm really excited, very excited of what Misha has between his hands now. On the single photon sources, that was spectacular by Quandela. We thought it's a mature technology now, and now the challenge is really on the packaging. It's really on really having the right fiber-to-chip coupling to actually integrate single photons into a photonic integrated circuits. On the detectors, we really have to go into further integration method. That's really a key challenge for all of us. Photonic integrated circuits is a very mature technology now, but I'm really quite amazed by the reconfigurability and the way that we actually can program them. And for me on that, the presentation from Ipronics and the presentation from QUIX has shown like a new paradigm shift on integrated photonics. And for those of you who spend a lot of days of the year talking about PICs, this is something really interesting. I love the presentation from IBM and really showing the maturity, but also really showing the openness to collaborate. This is 15 qubits that they're giving now for free. I like to say that word, for free. And also I really show the Q side, how they keep working, how keep increasing their supply chain, and how they are really almost there in the market developing the quantum random number generators. There are still challenges. There are still a lot of challenges. For me, the integration with UV waveguides, none of you had an answer. I heard today that there is a new platform on this, but the person didn't want to talk about it, so I guess it's still on stealth mode. And the single photon detectors to be integrated in the PICs is something that we still need to cover. Packaging, temperature control is something that would require a whole new meeting, and we have a meeting on packaging and temperature control at PI in November just to talk about this. We didn't talk about the electronics, which is still one of the things that we need to address here, especially the low noise microwave electronics and the control electronics. We need to deal with that part of the supply chain, which it was not part of this focus of this meeting, but many of you, and especially PTV as a user, saw this as a big challenge. So I think there is a lot of room to cover. There is a lot of collaborations. The purpose of this meeting is not to teach. The purpose of this meeting is to get to know each other and to find ways to collaborate. I honestly feel that AMO should talk to PTV. I honestly feel that Lionics should talk to Vexlum. I think Vexlum should talk to Icon Photonics. I think Quandela should interact a lot more with Toptica. There is a lot of collaborations to be done here. Just send me an email if you want to be introduced. The most important, continue collaborating, continue being epic. See you soon. Take care. Bye-bye.
See you. Bye-bye.